you see what we study, okay, how we study, why we study, and how we implement that in a real physical system. That's all. This thing is lacking. You understanding? The purpose of this presentation seminar is not just to teach you control theory, because it's a 50-hour session, correct? One semester, right? I cannot teach in 2 hours. Not required also. But you should understand that what you are studying is actually so useful and is actually so much applicable. Are you able to feel what I am trying to say? Yes or no? Try to bridge this, join these dots. You'll understand what I am trying to say. So, if you design a control system with its transient parameters, just giving a recap, if you design a system considering the transient parameters and do a stability analysis with a pole zero placement, something which you say you have studied, then I don't see why we cannot design control systems. You are understanding the application? So what I am trying to do now is, I am repeating it again so that you are very alert. What I am trying to do now is, you have seen the practical implementation of control systems, its importance in spacecrafts, the theory that you studied already. You say, I am trying to bring those simple equations which you read in your classroom, okay, with that real system. You yourself try to keep on mapping that, then you will understand the beauty of what you are studying. This is the graph that I was talking of. This is the step response, okay? So you have designed a system, you have a step response as the input, okay? But the output goes like this. This is a common graph which you see in your controls books. Have you? This is what we have been talking since the last 20 minutes. I have told you the importance of everything that is there in this graph, because this is what is designed. You see this peak overshoot, right? Design, because when I give an input, I should know what output it gives, correct? These are all unwanted parameters in the system. This should not happen, right? Get the point? This is happening because of unavoidable resonance in your system. So this we can reduce, and when I give an input, I should get the output quickly. If there is a delay, okay, then there will be a delay in response of the system. Suppose 2 or 3 systems are cascaded. See, no system is independent, right? Yes or no?
Yes.
There will be lots of interactions between 2 or 3 boards in a system. Boards means the circuits. Do you agree with me? So if a delay is introduced in one system, it will lead to additional delay in second system. Second system will cause some more delay. Third system, then you give an input, you will get output after 30 seconds. Understanding? Is it acceptable? No, right? Because your satellite should stable as early as possible. It should not happen 30 seconds after you gave the control signal. So we minimize all these things, and this is a steady state error. This means what? Your satellite should point 90 degrees with respect to the plane of the earth, okay? Whatever, launch vehicle or satellite, the theory is same actually. So if there is a steady state error of this much, that means what? Your launch vehicle is actually not 90 degrees with respect to the plane, which is risky. Yes or no? Correct, no? Because if the launch vehicle is huge, 50 meters, 1 degree will lead to a great offset in the top end. Am I right or wrong? Which can lead to a shift of mass, or the center of mass or center of gravity of the entire system, correct? So a 1 degree of error can lead to the launch vehicle falling on the ground. It's so important. You are able to understand what I am telling with this graph and how I am relating it with a real system? Yes or no? That is actually the real implementation. Okay, so I have talked about this, I have talked about this. So when you design a system, you consider all